Hello everybody, my name is 𝗂𝗏𝗄𝗿. I welcome you all to this webinar, Interactive Data Science, Visualizing Data with Dynamic User Interfaces. Let me first introduce my company. I'm working at the company 𝗨𝘀𝗲𝗿. It's a medium-sized software company based in Berg in Austria, Upper Austria to be precise. We have around 30 employees. From their background, they are theoretical physicists, software engineers, and data scientists. 𝗨𝘀𝗲𝗿 is a Wolfram technology reseller, and our main customers are Austrian universities, as well as the 𝗱𝘆𝘆 Gesellschaft in Germany. And as a reselling partner for Wolfram, we provide license and installation support from your order until the software is running on your machine. Furthermore, we provide technical support in using the Wolfram products. Of course, the Wolfram products, the functionality is huge, and we are not experts in all areas. So our technical support is limited to those areas where we can help you. For the other things, we just will refer to the Wolfram stuff. Our other business areas are data science, industrial mathematics, and financial mathematics. And furthermore, we provide consulting and project partnerships in data science projects and in Wolfram technology-related projects. If you want any additional information, do not hesitate to contact us. The email address is here. So this brings me to the main part of this webinar. First of all, small motivation. Why do we care about dynamic user interfaces? What are they good for? And here I have two examples, very basic examples. First examples is if we want to explore some data, you have just imported some data set. So let's generate a sample data set here with random data. So this is a random curve, and I have added an outlier at data point 64 here. And consider you have a huge data set, and you want to see more details. For example, have a closer look at the region around this outlier. Then you can use, for example, manipulate and interval slider control in order to interactively adjust the plot range. So you can zoom around in the plot, for example. This is the very first and basic example. The example 2 is finding, for example, appropriate parameters for pre-processing. Also, this here is a very primitive example. We have the same curve as before, and we want to apply some Gaussian filter with a radius, a smoothing radius, which we do not know beforehand which radius will be good or appropriate. So you can just play around with the radius and immediately see the result of the changed. You can make a better or more or less smooth curve. Okay. The first thing I want to show you is the Mathematica or Wolfram language construct called manipulate. For everybody of you who worked with Wolfram Mathematica before, manipulate is structurally very similar to the table command. So if you compare those two here, they are very similar. The first one simply creates a table of numbers from 1 to 20 with step size 1. And so to say, the manipulate here lets us view each of these table entries individually by simply providing a control for this variable here, for the variable n, and we can see here the individual table values. Of course, this is a very primitive examples. You can have here arbitrary mathematical expressions inside. So for example, also a plot command. And in this case, we have a simple sine curve where we can adjust the angular velocity and immediately see the effect of changing the angular velocity. Of course, you can use more than one variable in your manipulate. So for example, here I have a plot of 3 curves. The first is a stretched version of cosine, the second is a stretched version of sine, and the third curve is a linear combination of the first two. And I have here 2 controls for adjusting the stretching factor of each of those sine curves, and you can immediately see how the results change in the below plot. Of course, all Wolfram language constructs come with lots of options, and you can tweak the user interface and the appearance of the manipulate very nicely. So you can, for example, provide a custom label instead of displaying the symbol name W here, omega here. You can display angular velocity. And there are lots of different control types which are supported by default. So this is an example here where we just have several example variables. Each variable is of a different type or is using a different control type. So the first is a continuous interval. For this, you use only the variable name, an initial value, the display name. So here we see continuous interval is currently initialized with 0, and internally it's the variable with name A. And the range where we can adjust the parameter A ranges from 0 to 1. So this is a continuous slider, and here below we see the value of the variable A. If we want to have a slider with discrete steps, you can here use the step size. So the range is from 0 to 10 with step size 1. The third example, variable C, is a list selection. So if you do not provide a range but a list, you can pick one of the list items and store it to the variable C. It's initialized with item 1 here, as we can see, and you can simply select item 1, item 2, or item 3 and see the result here. It's a so-called setter bar here. This next example is a 2D slider. So you can have 2 interval specifications. If you have 2 interval specifications, you will get a 2D slider. And the variable D is a 2D point, which corresponds to the currently selected point on the 2D slider. Of course, you can have Boolean values, so it's a list selection with true and false, the special variables. In this case, you will not get a setter bar, but a checkbox, a primitive checkbox. If you provide colors, you will automatically get the color slider. And you have also an input field where you can place arbitrary text or even mathematical expressions which are even evaluated. Integrate sine of x 0 to 1 as an example. Would have something happened here. It's from 0 to 1, so so here you can place also arbitrary mathematical expressions and assign them to your variable g here. The next thing is you can even use your own controller in function here. So in addition to those default control types, you can here place arbitrary functions which specify the control you want to use. In this case, I have an interval slider. The interval slider will get this first argument on the variable which is to be manipulated. It's x range, and those are just the additional arguments for interval slider in order to specify how it will be displayed. So it's a range from 0 to 100, and the minimum interval size is 10. So if I just slide around here, you can change the upper and lower limit, but cannot make the range smaller than 10. The next example is a toggler bar, for example. A toggler bar is similar to a setter bar, but it allows multiple selection of multiple items. So it's good for choosing values from a set. There's only one thing to remember, that the order of the items really depends on the order of your clicks. So it is not automatically sorted. If you want, so to say, a canonical set representation, you should sort this list then. For a full list of available controls, I have put a link to the Mathematica reference here. There is a whole guide on this topic, and also there are 2 tutorials for introducing manipulate and also advanced manipulate functionality. Sorry, I have to mute my phone. So the second part of this talk is about the dynamic construct. It's a more primitive construct, but allows you to create more sophisticated dynamic user interfaces. Manipulate is so to say the high-level construct, and dynamic is the more low-level construct. So in order to introduce manipulate, consider a simple variable. Here we have a variable which we assign the value 1. And no surprise, if you evaluate this variable named value, you get 1. And this output here does not change if you at a later point in your Mathematica session assign a different value to your variable. But you can, if you want to, instruct the front-end or Mathematica front-end to update those outputs as soon as the value changes. And in order to do this, you wrap the variable in the dynamic construct. So if you evaluate it in dynamic, the output looks just like the same as if you said only, please evaluate value. But in addition, if you then at a later point in time change the variable value, this output here will automatically be updated. One additional thing and important thing to know is that you can use dynamic value not only for output, but also for input. So consider, for example, a setter bar, which takes its first argument, usually a variable, wrapped in a dynamic construct. And here I have the list from 1 to 10. So range at 10 is nothing else but the list, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can change the value of the variable you passed in this dynamic here by just clicking the setter bar. And you see that those changes reflected here as well. No questions so far. Good. So then I will go on. Here is another example with a slider. But we can use dynamic not only for primitive variables, but also for arbitrary language expressions. So if you should have evaluated those two first. So here I adjust the variable value again dynamically, and below here I want also always to see the square of the value. So 10 squared is 100, etc. And you can all have arbitrary complex mathematical expressions here, for example, also a number line plot, and you see this adjusted interactively. So in order to understand what dynamic actually does, it is important to know several things. It's a bit technical now. I hope this is okay for you. So every mathematical function has so-called attributes, and let's see what the attributes of the dynamic mathematical function are. One of those attributes is named hold first. And what this means is that the first argument which will be passed to dynamic will be in hold form, so it will not be evaluated. Instead, the mathematical front end is responsible to evaluate the parameter of dynamic, and the front end decides when to do it and when to display the dynamic value. So how does this work? Whenever the front end notices a change to some variable which is used within the expression passed to dynamic, it will re-evaluate this expression. If the variable is named x and it is contained in the expression, not wrapped within a more deeply nested dynamic, so you can also nest dynamic constructs. And it will only re-evaluate the expression if the dynamic is currently in a range which is visible to the user. So if you have a larger notebook, or you put your notebook somewhere in the background, the Mathematica will not evaluate your expression. And this can have nasty side effects if you are using, it can have nasty effects if you use dynamic expressions which have side effects which you rely on. So it is therefore discouraged to use expressions with side effects within dynamic. One additional thing to know is that there is synchronous and asynchronous dynamic evaluation. Also here it is a bit technical. The Mathematica front-end and the Mathematica kernel are two different processes, operating system processes, which communicate via three so-called communication links. There is the main link, which is used by the front-end whenever the user enters a new expressions, and the front end sends this expression to the kernel via the main link. The service link is used by the kernel to send back to the front end the evaluated results. And the third link is the so-called preemptive link, which is used by the front end to evaluate expressions related to user interface rendering. So these and the first two links are for asynchronous evaluation, and the third link is synchronous evaluation. This means that if you have, for example, a dynamic variable or dynamic expressions which the front end notices which is now to be evaluated, it will send it over the preemptive link to the kernel and will wait for the answer in order to display the dynamic value. And as long as this computation is running, the front end is not responsive. So what you should take away from this is that, okay, it's here, but dynamic expressions are evaluated synchronously using the preemptive link. And I have an example here, so to make it clear. I have again a variable which I can set from 1 to 10. And here I have a simple expression which takes quite a time to evaluate. I'm simply using the pause command for this purpose here, for demonstration purpose. So if we try to evaluate it here, we will hit a timeout. And notice I try to click the toggle bar here and nothing happens. Okay, well, that's not true. Just Mathematica crashed. This is not good. So let me have a look. So changing the screen environment to slideshow. Here we are again. So yes, I want to evaluate all initialization cells. I have again here the setter bar. And let's try it again. If I click here, nothing happens because Mathematica is still waiting for this expression to evaluate. And we see here the notice aborted. This is because by default, I think dynamic will abort the computation after 5 seconds if nothing comes back from the kernel. And it is only after this 5 seconds the user interface gets responsive again, becomes responsive again. You can adjust this time limit using a dynamic option here, an option of dynamic. But this adjusting the time limit will not always help. And it may happen if you are just developing dynamic controls. Sometimes there can be situations where you run into some infinite update loop if you have complicated interdependencies between dynamic variables, which also can cause the front end to freeze irrecoverably. So it's those low-level constructs have their complications as well. A good solution is if you have such complications and expressions which take long time, you should use the dynamic option. You should disable the synchronous evaluation by using this option here. So setting synchronous updating to false. I think I should speed up a bit. So if you used synchronous updating false, then Mathematica will also use the same evaluation type of evaluation which you use by default. So it will also evaluate it asynchronously using the main link and the service link. So you can interactively change the variable. It's not freezing anymore, but you see here that the computation here is running. And if you wait long enough, it will finish and then update this dynamic value. In general, it is a good idea to use asynchronous dynamic evaluation for all expressions which cannot be evaluated in 1 second or so. One additional thing to say is that if you want to develop reusable dynamic controls, it's important to keep your variables bound to local scopes. It's the same thing as in every other programming language. Your variables should be not, the scope of your variables should be as local as possible, and global variables are not a good idea in general. The same thing applies to Wolfram Language as well. And Wolfram Language provides several different scoping constructs. There is the block construct, the module construct, and the dynamic modules construct. For the block and module construct, I refer you to the documentation. And for dynamic controls, the dynamic module is usually the right to choose, because to illustrate this here, if you have a module, this will generate an anonymous context or anonymous namespace for the variable x, which is these $4998 in my case here. And if you, for example, copy and paste this command, this control, you have the same scope here. So those two controls are then interlinked, which is usually not what you want. If you have a dynamic control, you usually want them to be independent of another. And if you use the dynamic module, it is the front end which actually decides with the scope of the variable x, the variable. So the scope of this variable is really bound to the control itself. And if you copy the control, you have really a new control with its own variable x. So those are not interlinked anymore. And this is the reason why you should rather use dynamic module instead of module. Mathematica will also give you a hint on this because it displays those variables here in red. The last useful scoping construct is the with construct. It's sometimes useful in order to work around this hold first attribute of dynamic. So consider, for example, you have a list of variables and you want to have individual controls for each of the elements of this list. How could you do this? The solution is here. It's a bit it looks like a bit complicated. I will go through it in a moment. So if you have, I should, it's here. So if I just adjust the first slider here, I am adjusting the first element of the list, the second element, third, fourth, and fifth element. And how does it work? I create a table of tuples with I and slider, so the index from 1 to 5, and those are those 5 things, and the slider here are those controls. And if I do not use this with construct here, what I get is a problem, because I'm trying it here. If you use table with dynamic list I, Mathematica also gives you a hint that this is a problem. Then, because dynamic has an attribute hold first, this I here will not be evaluated. What you get is really a list of dynamic list with a symbolic name I here, and the I will not be inserted here as you want to. However, if you use the with construct, with is, so to say, similar to replace all. then this replace all will really replace the symbolic names with the corresponding index. And this is what I'm doing here, and this is why this here works. Here I have additional references for you. There are several tutorials on manipulate, on advanced manipulate functionality, a tutorial on advanced dynamic functionality, and also the introduction to the control objects, some of which we have seen, like the setter bar, the toggler bar, the control slider control, the 2D slider, etc. Okay, I have now two more practical examples in other notebooks. Let me have a look. It's the big list plot and the zoom control. Let's start with the zoom control. Or let me just ask you, are there any questions so far? Okay, chat window is empty, so I'm continuing. So the first example here is, consider you have a 2D graphics object like a Mathematica plot, a list plot, or a graphics. For example, also a Mandelbrot set plot is a possibility of such a 2D or an instance of such a 2D graphic. Now it would be nice if we just could interactively zoom in, right? We can build our own zoom control the following way. I will go through this code in a moment. Just try it out. So what this zoom control does is it lets you click on the graphic and drag a zoom region. And it will zoom in. And if you simply click without dragging, then you will reset the zoom range to the original zoom range. So this is nice. Another example here with the Koch curve. As you can see, it works nicely. So how did I do it? Let's have a look at the code. The zoom control takes one parameter, namely the graphics you want to zoom into. And it is implemented by using a dynamic module. So here we declare all variables which are local to this new control. The variables we have here is the initial plot range, the current plot range, and those two mouse points. The point 1 is the point where you initially clicked, and the point 2 is the point where you released the mouse. Those two can be equal, then you have clicked, and if they are not equal, then you have a rectangle and a drag and a new zoom region. Then I have two functions which are called, those are initialized here, which are called when the mouse the mouse button is pushed down, and another function which is called when the mouse is moved, and another function when the mouse button is released. So those are these three functions. We come to it in a minute. The first thing which happens is that the initial plot range will be set. It will be taken from the graphics by using absolute options and lookup. So with this construct, I'm just asking the graphics, what is your current plot range? And I'm storing it to initial plot range. Moreover, I initialize the current plot range also to initial plot range and set those two mouse points to the special variable, to the special value null. Okay, and how does it work? When the mouse is pushed down, I'm storing the current mouse position, which is relative to the enclosing graphics object, to the variable p1. This is simply the mouse down function. When the mouse is moved, I'm storing the current mouse position to P2 if P1 is already set. Right, if the mouse cursor is released, then I have three cases, or two cases to be precise. The first case is that P2 is null, then you have just clicked. Then I'm resetting the current plot range to the initial plot range. And if P2 is not null, then you have really dragged a region, and both P1 and P2 are mouse positions, valid mouse positions. Then I'm setting the plot range to the position P1 to P2. And then finally, I'm resetting P1 and P2 to 0, to null. How are these variables now used? Here comes the actual control. It consists of the graphics, of course. The graphics is wrapped in a show construct in order to adjust some of the options of the graphics object. The options which are adjusted are the epilogue. The epilogue allows you to draw on this graphic some other additional graphics primitives, namely this dashed blue rectangle with the mouse position. And the second option, most important option here, is the plot range, which is here the current plot range variable. Both are wrapped in a dynamic object. And all of this is wrapped within event handler, where I'm instructing the Mathematica frontend when the mouse is pushed down on this control, then please call this function. When the mouse is moved, please call this function. And when the mouse is up, mouse button is released, please call this function. And this is how this really works. Again, if we also try it here with the Mandelbrot set plot, you can see that it works, but it's a bit, the resolution is a bit bad, and we can also improve this. What would be necessary in order to be able to adjust? Or first, why is it that the resolution is bad? Because the Mandelbrot set plot by default uses a computation range, this computation range you see currently, with a limited resolution. And if I zoom in, it does the same computation for the whole range, but only displays this tiny fraction of the image. What would actually be necessary is it would require to wrap the Mandelbrot set plot itself into a dynamic object and pass the set min and set max option to the Mandelbrot set plot in order to get a better resolution version of the image. So this is why I have a second and improved version of the zoom control. The difference is that the plot range, which was a local variable before here in the dynamic construct, is now passed from outside. So if you have a look at the definition of the zoom control version 2, it takes the plot range as parameter that wrapped in a dynamic dynamic construct, and takes also the graphics. Most of the things here are exactly the same, with one slight exception, that instead of show, I'm using dynamic show. This has a technical reason, because if you pass a dynamic graphic, then show will not be able to handle a dynamic graphic. So what dynamic show actually does is to move this dynamic takes this dynamic graphics and pulls the dynamic outside of show, so to say. It simply transforms the dynamic the show dynamic to dynamic show. Okay, the rest is the same, and I have also a default version here, if you use dynamic show without the first argument, without the plot range, then it will create, it's here. If you use the zoom control without the plot range, then it will simply create here a local plot range and use the zoom control as before. So this allows now to use the zoom control version 2 as before. In this case, I'm passing just the plot to zoom control without a custom variable for plot range. It will be created here automatically. And also for the Koch curve, again, if it works as before. And here is the last example. I'm now using a dynamic module and initializing the plot range to this range. And now using the zoom control and passing my custom plot range to the zoom control, and also using the dynamic value of plot range here in the Mandelbrot set plot. So I'm making a dynamic Mandelbrot set plot and pass here the plot range accordingly, so that the Mandelbrot set plot really produces a high resolution image for the region which I am interested in. Okay. You will get all the notebooks, as I said, after the webinar, most likely in the course of tomorrow. And you can have a look at the code and use the function in your notebooks if you like them. Okay, then if there are no questions, I can move on with another example, practical example. Namely, how do we visualize large data sets interactively? In order to start, I'm just generating, I would say, a small-sized data set, a data set consisting of 10 variables. Each variable is simply a list of random variables. So this is the data set I created. I have an index column, which just and a time column where the seconds are incrementing. And then I have 10 variables here with more or less random real values. Note that the data format of this generated data here is equivalent to using semantic import with the form argument named columns. So now let's plot the data. How do we do this? In order to transform this data set into a form which is accepted by listplot, I'm using here a small helper function. It really transforms the data set into X and Y values. And the arguments to this helper function, I called it plot data here, is my data set here, which we can see above, and then the name of the variables which I want to use in X direction, and the variables which I want to see in Y direction. So this is a single variable. It's either index or time, and the Y keys are a subset of those 10 or 8 variables here. It's 10 because it doesn't display everything. So it's a subset of those 10 variables here. And for this selection, I'm generating the plot data for the list plot. So if we want to see what plot data really does, it takes quite long. So for each of the variables, if I'm using the index column, I have here always the index as first list argument everywhere, and all variables. So I get a data set with all variables, and I can pass it directly to listplot, and listplot will display nicely my data set. Okay, this is my data set. I can also use datelistplot, but passing as index variable the time variable. It's the same graphics, but with different x-axis. And moreover, we can reuse our zoom control, which we defined in the example before. So it's the same command here, but I'm just using the zoom control command here. And I can have a look at some more details. The same with datelistplot, I will skip it. Okay, so what else can we do? We can make our plots also interactive. We can let the user select the variables which he wants to see. So for this purpose, I'm assigning fixed colors to each of the values, to each of the variables, so that if I remove variables, the colors do not flip around and the user. So for one variable, really the same color is used, regardless which variables are currently selected. So this gives an association of variable name to color. And I can now use a manipulate control. It takes a while. So I have here one of the variables of the manipulate is the x variable. It refers to the name of the variable which is to be used in x direction. It can be either index or time. And as we saw in the initial presentation, if you're passing here a list of values, then you will see here a toggle bar. If you change to time, then the x-axis is replaced. And time is displayed here. And also you can select the variables which you want to see. So let's display just variables 1 to 5. I can deselect them here, and if I wait a little while, then some of the curves will disappear. I guess the screen transfer is taking much of my CPU power. So this is why it takes quite long. And I can use the zoom control here. One thing which is not so nice is if I now change and also remove variable 5, the zoom range is now reset. How can I do this? It's again by moving the plot range variable outside of the manipulate so that it lives longer. Right. It's the same control, but just with the Y variable selection. And if I'm now zooming, right. The zoom range is retained even if I change the selection of Y values. Okay, it's just 10 minutes to go, so let's skip. For plotting larger data sets, I have here an example. with 50,000 plot points per variable. And this really takes long and makes interactive interactive display of the dataset impractical. What you can do is, for example, using interpolating functions instead of the data directly, and to use plot instead of list plot. So with this trick, with this trick, I think I will skip this computation here. Really, the screencast seems to take too much of my CPU power. So it took 59 seconds. That's really long. And for plotting the same data set with interpolated functions, this is this example here. It's significantly faster, 4.9 seconds. But before I go on, I will slightly reduce the dataset size, because otherwise this presentation will last too long. And I have done the same as before, so same control, same data with same type of plot with larger data set, and with same type of interactivity. For plotting still larger data sets, let's remove it to say 500,000. What could we do here? One approach would be to downsample or error resample the data set, but this has the obvious drawback that if you are interested in seeing outliers in your data, they are potentially lost and not displayed in your plot. So what I'm showing here is an approach which works the following way. We partition the data into sublists using partition, and for each of the sublists I compute its minimum, medium, and maximum. And instead of displaying the original data set, I'm displaying the curve of the medians and displaying, so to say, an error range around the median corresponding to the minimum and maximum values in those partitioned sublists. I have several helper functions again, and reduced plot data. So with this approach, yes, maybe I'm showing this here. So the data set which is now displayed is of the form around. So there are not primitive real values, but mathematical around values. These are special constructs which represent a real value with error bars around it. So, and a list plot luckily has a nice built-in capability of displaying those error variables with error values. So you see here, if I slightly increase it, this downsampled data set with 500,000 data points for each curve, and the minimum and maximum values are retained. And the nice thing here is that if you zoom in on this graphic, then the resolution of those sublist binning is adapted. So if you zoom in for here for example, and wait a little while, you will see that the resolution gets better. And if you even, this is maybe good. Go back. Here's a more interesting region. Okay. I think this brings me to the end of my talk. There are only 2 minutes left now. I will start the Q&A session now.